over time, not over the sort of support of the window period distribution. Well, then it turns out that this biomarker approach is not actually estimating current incidence, but a weighted average of incidence in the past, where the weight function actually has to do with the time weight function that's weighting incidence in the past is the factor of recurrence density, which is basically the survival distribution of the window period divided by the window period. So basically here, what's happening is we use this cross-sectional sample. We use this biomarker approach. We think we're estimating incidence here. We're not. What we're doing actually is estimating a time-weighted average into the past, going backwards in time, where this weight function is this backward recurrence density. So I'm looking backwards in time here. Now the mean of that backward recurrence density, I'll call the shadow. So the shadow is the mean of that distribution. And a little Taylor series expansion shows that approximately what we're estimating by the biomarker approach is not the current incidence here, but the incidence here. We're estimating the incidence at the shadow with a time lag, where that time lag is the shadow. So what is so a little bit about these shadows. We call it a shadow because the biomarker is not estimating current incidence, but a time in the past by how much time by a shadow that's that's being cast by the shadow, a time lag into the past. Now, the shadow is the mean of the backward recurrence time of these window distributions, and it can be shown that it just involves the mean window time and the coefficient of variation. Basically, the tail of the distribution comes into play here. And the shadow gets bigger as the mean gets bigger, and also as the coefficient of variation gets bigger. It's the coefficient of variation of the window period distribution. So there are a couple of implications of this theory. The first is about designing assays. We want a good assay. So what's a good assay? We want an assay that has small window period, small shadows, because that means we're estimating incidence closer to the current time. So this is shows you the maximum coefficient of variation one could afford, and still have a shadow, say, within 1 year. Let's make that our principle, a shadow within 1 year. So if we have a mean window period of 0.5 years or 6 months, you can afford a coefficient of variation of 1.7. The smaller the window period, mean window period, the bigger the coefficient of variation that you can afford and still have a small shadow. But it comes at a price. And the price it comes with is the sample size. If you take your mean window too small, you need a bigger sample size to get the same statistical level of statistical precision. So it's the familiar trade-off that we've seen a lot in statistics. It's a trade-off of bias and variance. The second implication of this theory is what is the impact of the tails. The tails of the window distribution. The concern here is that there are groups of people called elite controllers or viral controllers. These are people who have suppressed viral loads, and they're not making any antibodies, so they might stay in the window period for very, very long periods of time, maybe until AIDS, when they're taken out, or maybe until death. Maybe they, as elite controllers, are thought never, a very, very small number of people never develop AIDS. So what's the impact of this, of having very long tails on the window period? So one way to look at that is a mixture distribution, where you have a group of people who progress through the window period relatively fast, that's the bulk of people, and a very small number of people who are slow progressors who may stay in the window for very long periods of time. So you have a certain proportion in this group and a certain proportion in this group. You can write down the window period distribution for the combined group, And then you can write down what the shadow is in terms of that mean of the backward recurrence time, which involves the mean and coefficient of variation of the two groups. So here's the results of some of those calculations. This is a yellow group mixed with a blue group. The yellow group has a mean window of about half a year, and the blue group are people like viral controllers who stay in the window period until the development of AIDS, maybe 10 years. So a mean of 10 years. These coefficients of variation were chosen to match the window period for the BED assay that's been reported in the literature and also the time for AIDS distribution that's been reported in the literature. And this shows the mixing proportion. The key point here is that even if only 2% of people are in the blue group, the shadow is about 2 years. It means we're not estimating current incidence, but we're estimating incidence about 2 years ago. Here's another calculation, more extreme, of elite controllers. These are people who may never develop AIDS, and they stay in the window period until death. They have very low viral loads. And here I'm showing you the calculation. It was just a tiny bit of contamination with elite controllers, even just 0.5%. And with just 0.5%, even though the mean window period is half a year for 99.5% of people, even if just 0.5% are in the blue group, the shadow is about 2.5 years. So even this small contamination has a big effect on what you're estimating with the biomarker approach. So now let's go back to the Zimbabwe controversy. Now remember, this was a controversy that said, well, wait a minute, the biomarker incidence that was calculated was higher than the cohort estimate in the study of new mothers. Now provides a little bit of insight what's happening. You can get a shadow of over 2 years is produced with only 0.5% of people who are elite controllers. So if you go back these are new mothers. So if you go back 2.5 years, what the biomarker approach is estimating the risk of women during the prepartum period, not during the postpartum period. And during the prepartum period, clearly they were sexually active, going to be at higher risk of infection. In the postpartum period, there was counseling going on and so forth. So this helps to explain the discrepancy that we've seen between the biomarker approach, which is estimating incidence slightly in the past, and a cohort approach, which is estimating it forward in time, which may also be contaminated by counseling and other educational kinds of programs, distorting the sort of the background incidence. So this issue of the biomarker versus the cohort. Neither is the gold standard for the other. They both have issues, and I think through some of the statistics we can get some insight into why we have these differences. The accuracy of the biomarker assays for current incidence depend both on the mean window and the coefficient of variation, the tail of the distribution. It's a trade-off between bias and variance. Important point is that is a good example where I think tiny changes, little changes in the tails of the distribution of that have big implications. So the challenge that we face is what to do about this. Well, I think one thing is we can design better assays to try to protect yourself against the tails. So this is some calculations for that mixture model that I showed you with elite controllers, and showing you how to pick your parameters for your optimum assay. So the mean of the you can get to titrate some of these assays, these like tuned ELISAs. You can titrate them to get the mean window period to be what you prefer, whatever your cutoff is. You can change the cutoff. And what this is showing you for different percentages that are elite controllers, people who have very long window periods, how to choose the optimum window period if you want to minimize the shadow. And so, for example, just focusing on this curve, 99.5%, only 0.5% of people are elite controllers. Turns out that there's a minimum, a way to choose it so you get a minimum shadow. And here it's about a 1.5-year mean window period produces a minimum shadow. And what that means is it gives you an estimate that's more relevant or more current than choosing another cutoff or window period.